Hello and welcome to Biology Doodle. Today we will be going through the citric acid cycle, which is the second step in aerobic respiration following after glycolysis. So let's jump right in. Step 1, just over here, we have acetyl-CoA from the oxidation of pyruvate adds its 2-carbon acetyl group to oxaloacetate, producing citrate. Step 2, citrate is converted to its isomer, isocitrate, by removal of one water molecule and addition of another. Step 3, isocitrate is oxidized, reducing NAD+ to NADH. Then the resulting compound loses a carbon dioxide molecule. Step 4, another CO2 is lost, and the resulting compound is oxidized, reducing NAD+ to NADH. The remaining molecule is then attached to coenzyme A by an unstable bond. Step 5, probably the most important step in the citric acid cycle, CoA is displaced by a phosphate group, which is transferred to GDP, forming GTP, a molecule with functions similar to ATP. They're both high energy compounds basically. GTP can also be used as shown to generate ATP. Step 6. 2 hydrogens are transferred to FAD, forming FADH2 and oxidizing succinate. Step 7. Addition of water molecule rearranges the bonds in the substrate. And step 8, the final step, the substrate is oxidized, reducing NAD+ to NADH and regenerating oxaloacetate. So we're back at the start now. Just as an overview, some things to keep in mind here. In the blue we have the carbons and how the carbons are changing as we go along. So this is something that examiners like to ask a lot. So acetyl-CoA, 2 carbon, goes to oxaloacetate, 4 carbon to make 6 carbon citrate. Then we go to isocitrate, that's another 6 carbons, but then this important step is alpha ketoglutarate from isocitrate. We lose that carbon in the form of carbon dioxide. So keep that in mind, step 3, that we lose a carbon there. And then once again, in another blue, from alpha ketoglutarate down to succinyl-CoA, we lose another carbon in carbon dioxide. Also, in the kind of lighter orange colour, you'll see that we have NADH plus a proton. We have 3 of those made. So here, here, and here. Very important again, these are high energy compounds that we are going to bring into the next part of aerobic respiration, which is oxidative phosphorylation or the electron transport chain. Another important high energy compound that we're going to have is FADH2. Again, we're going to bring that in to the next part of aerobic respiration, and probably the one that you're most familiar with, ATP, again, is the most important energy molecule in our systems. We use it all the time, and again, we are going to use the other high energy compounds to make more ATP in oxidative phosphorylation. And those protons that you see with the NADH are so important because they drive the proton motive force in oxidative phosphorylation. So we're just going to go to an overview now. So keep everything in mind. Let's move on. So here we are in our overview. Now, this is so important. This is the most important thing that you're going to get out of this, is per 1 glucose, because as you'll remember from glycolysis, we got 2 acetyl-CoA. So the citric acid cycle happens twice, and this is so important because a lot of times when you're in exams, examiners will say per 1 glucose molecule, how many whatever do you get from whatever stage of respiration. So in the Krebs cycle, per 1 glucose we have 2 ATP, we have 2 FADH2, and we have 6 NADH and 6 protons, which are all going to go into oxidative phosphorylation or the electron transport chain. Okay, so I hope this was helpful. Check out Biology Doodle on Instagram as well, and don't forget to like and subscribe. Leave a comment below if you have any other questions. Thanks. Bye guys.